Then we're going to talk about a slightly different equilibrium constant that's called Kp.
All right, for gases, we can define what's called Kp, which works very similar to Kc, just using partial pressures in atmosphere. So we do want to be mindful it does need to be in atmosphere. When we were defining Kc, we used the brackets, which always meant molarity. Here you can see we do just use pressure, but it is implied that it's supposed to be in atmospheres. But otherwise, it works in the same way. We have our products on top, we have our reactants on the bottom, and the coefficients from the balanced equation are exponents on the pressures in the equilibrium constant. And so it works in much the same way as Kc. It just has we're just using, the only difference is we're using pressures in atmospheres, not concentrations in molarity. Now I want to do an example where we look a little bit at the quantitative side of Kp, using the number itself. So the reaction 2N2O5 becomes 4NO2 plus O2. Once equilibrium is reached, the pressure of N2O5 is 2 atmospheres, the pressure of O2 is 0.296 atmospheres, and the pressure of NO2 is 1.70 atmospheres. What is the value of Kp? So we can start by asking, what do we want? It's the value of the equilibrium constant. So this is important. We don't want to not forget that equilibrium constants are numbers. Equilibrium constants are numbers, and they have values that we want to be able to compute. So if we want a number, what's the equation that relates to this number? Well, it comes from the reaction. We're given the reaction, so we need to take that and turn it into the equation for Kp.
Okay, so in this case, I want the value of Kp. So previously we've dealt with coming up with equations for Kp. Now we want to use one of those equations to get a number, right? To get actual value for our equilibrium constant. So it is a little bit different this time that it's Kp. What that just means is when we're coming to create our equation, it's still going to be the same idea that it's ratio of products over reactants, but we just use the pressures instead of concentrations. Kc, the C stood for concentration, Kp, the P stands for pressure, NO2, and then we still raise it to the same power. So that goes to the fourth power, pressure of O2 to the first power, and then the pressure of N2O5 to the second power. And we got atmospheres all over the place. That's one of the things when we're working with Kp, we do need the pressure in atmosphere. With Kc, our pressure needed to be in molarity. That is common, but we do want to be, those units are always tied to it. Okay, so Kp, we just go ahead and plug them in. NO2 is the 1.7 to the fourth. Pressure of O2, 0.296. And then finally 2.00 atmospheres squared. And so when you're working through this, you can multiply all that out, and the numbers would be 0.618. You will note there are a bunch of atmosphere units on there. Those just go away. They don't cancel how we've written this. There is an additional level of complexity to equilibrium constants that is where the units go that we're not going to be worrying about right now. So for now, we're just going to say when you plug in values like this to get the value of Kp, you've gotten the number. You've got that number. The units just kind of disappear. So we're going to say these pressures need to be in atmospheres. So if you're solving for pressures out of this, you just would need to know it's in atmospheres, and the K is going to be unitless. Equilibrium constants are always unitless. They're just a ratio describing that sort of kind of relative amounts of your products and your reactants, but there's not going to be any units on there. No participation questions in this video, but this is the halfway point. We got another 3 videos left to go in this set. Looking for more questions on participation 213. I'll see you in the next video. Bye.